So I hope everybody's having a good week. Weather's been cooperating, right? It's really nice to go out to the car and not melt. So let's get right into our lecture here. I'm going to pin this and let's talk about what we're going to do tonight. We're going to continue our discussion that we sort of started on Monday, where we're going to talk about building a circuit that actually adds binary numbers. So this is where the rubber really meets the road, folks. This is where this sort of abstract notion of a circuit that we draw with O's and ones becomes a real machine that does work. And the simple work that we're going to learn to do with a circuit tonight is we're going to learn to correctly calculate the sum digit and the carry digit when we add two binary digits. So just as a way of review from last time, when we add O plus O, we want to get O, don't we? And when we add O plus 1, we want to get 1, which we can write as O1, of course. And 1 plus O, we're going to get 1. And then finally, when we try to add 1 plus 1, we realize we really need that carry digit. It's the 1, and the sum digit is O. Okay? So our goal tonight is to build two circuits. They're called full adders and a half adder. We're going to build both of these. And then our goal is to then understand, hey, the circuit that we built really does correctly add these digits. I just want to point folks to the new material that's in the Good Stuff column. Somebody asked for some worksheets, so I have started to post worksheets in a folder called, obviously, Worksheets. Check them out. Solutions are included to some of those worksheets, and they can give you the extra practice that you're craving if you just can't get enough of discrete math, right? So what we want to do is we want to add P plus Q and get the correct sum and the correct carry. And in the black box world, sometimes we just draw a circuit as a black box. We're going to name this circuit a half adder. And the input is two binary digits, a P and a Q. And the output, of course, is a carry and a sum. So I want to just talk you through this, this work of building a circuit that actually does something. Okay. We're going to keep this at the top so that we can refer to it. Because that's the work that we want to do. So let's just look at what's going on here. One of these sums is different from all of the others, and that's this last sum when we're adding 1 plus 1, because it's the only sum that requires what we would call a non-trivial carry digit. O or 0 is considered trivial in some sense. So for all of the other sums, the carry digit is an O. But for 1 plus 1, the carry digit is non-trivial. It's a 1. So we're going to just use AND gates and OR gates and NOT gates to build a machine that will perform this operation of binary addition. What gate do we have at our disposal that can add a 1 plus 1 and give us this correct carry digit of 1 in the only case we need a 1? What gate would detect when the input is a 1 for P and a 1 for Q? Anybody?
And
That's right, Ronnie. The AND gate. Right? The AND gate is the gate that detects when we're inputting two ones. So our observation number 1, as we go through this process, is to realize that the AND gate correctly detects. Sorry, that should be detects. P equal 1 and Q equal 1 to give the correct carry digit. So we can start off just by figuring out the carry digit is pretty easy, right? Here we go. So P and Q are our inputs. And if we run them through an AND gate together, that AND gate is going to correctly detect when both of these inputs are 1. Do you agree? So we can say, hey, the output from the AND gate is going to work for all 4 of these, because if P and Q are both O, of course, the AND will output an O, and that's the correct carry for O plus O. The AND gate also will give an O if the inputs are of opposite value, and one is a true, one is a false. One is hot and one is cold. And it gives the correct output if we're adding 1 plus 1 for the carry. So the carry's easy. But here's our hope. Our hope is now to build this circuit out so that it can do more than just output the carry. We need it to output the correct sum. So let's take a look at what's going on with the sum digits, okay? When we're adding O plus O, the sum is O. When we're adding 1 plus 1, the sum is O. But when these two have opposite truth values, these two inputs, P and Q, are of opposite value, then we want that sum to be 1. So can you imagine what gate might at least output the correct sum for these two middle cases when the input is a 1 and an O?
Or.
Did I hear somebody say the OR gate?
Yeah.
That's right. So the question is, can we use the OR gate to get the correct sum digit? In other words, let's just expand our, we're going to build this up, okay? So let's just keep going. So we have P and Q as our input. We know when we run them through an AND gate, we get the correct carry. We'll keep that because it's working just fine. But if we take the P value and the Q value, so here they are, and run them through an OR gate, let's check when that actually works out. Okay, so we know it's going to work out for these middle two cases because if either one of these is a 1, the OR gate is going to output a 1, and that's what we want for the sum in these two middle cases. Does it work for the case when P and Q are both O? Does it give the correct sum? If we feed an O through an OR gate with another O, do we get the correct sum digit?
Yes.
Yes.
We do. So the only kind of issue is, hey, when we feed a 1 and a 1 through an OR gate, do we get the correct sum? We do not, because this is not the XOR gate. So this works for P equal O and Q equal O. It works for P equal 1 and Q equal O. And it works for P equal O and Q equal 1. This might be a tiny bit different than the notes that are posted, but it's these 3 cases that this OR gate works. But it's not working to correctly output an O for the sum digit in this 4th case when we're adding 1 plus 1. So somehow we're going to have to tweak this. We don't want to lose the functionality that we've just found, but we need to somehow inform the circuit. of the one situation when P is equal to 1 and Q is equal to 1, for which the sum digit is not correct on the output wire of this OR gate. Right? Somehow we've got to somehow tweak this output of this OR gate to make it work for all 4 cases, because we don't want different machines to do different problems. We want to build a machine that will add 2 binary digits correctly no matter what they are. Got it? So somehow we've got to use the information that's up here on this AND wire to inform and temper the output of this OR gate to make it work in this 4th case where it's not working. Does anybody have any ideas about how we might use the hot wire that is there when P and Q are both 1 to somehow temper this output, which right now is a 1, but we want it to be an O when P and Q are both 1. See, because the P and Q are both 1, we have a 1 on the carry output wire, which is good, but we have a 1 on this OR output wire, and that's not good. Any ideas?
You could add a knot.
Yes, that's exactly right. Let's somehow feed this information through a gate that's going to give us an opportunity to temper or change the output for the sum digit from being a 1 to being an O. So if P and Q are both 1, we know the AND gate outputs a 1, but this NOT gate is going to flip that to an O. How can we use the O that's on this NOT output wire to temper or change the 1 that's on this OR output wire to make sure our sum is O when both P and Q are 1? What gate could do that work?
An AND gate.
That's exactly right. If we feed the output from the NOT gate, and I'm going to scooch this over a little bit because I'm going to need a little more room because we're going to check this, but that's exactly the right intuition. If we feed the output from this NOT gate, which is going to be an O, if P and Q are both 1, through an AND gate with this 1 that's coming out of this OR gate, and this 1 is wrong for the sum digit. When we AND it with an O, we will get an O. Now let's just check this thing, right? We want to actually check it and make sure that this didn't screw up the stuff we had before. I'm going to make this a little longer so we have room to check all 4 cases, okay? So let's do the first case in green. When P is O and Q is O, okay? We want the carry and the sum to both be O. Are you with me? So an O comes out of the AND gate, and that is the correct carry because we want a carry of O. An O comes out of the OR gate. The NOT gate flips this O to a 1. And when we run the O through this AND gate with the 1, we do get an O out. And that is what we want, isn't it? Now let's check it for P being O and Q being 1. Let's see if it works for that. What's the output of the AND gate when P is O and Q is 1?
O.
It is O, and that is still the correct carry. What does the NOT gate do to that O?
It makes it a 1.
It does. It makes it a 1. Now let's run an O and a 1 through the OR gate. What's the output? 1, right? O or 1 is 1. And now when we feed this 1 from this NOT wire through this AND gate with the 1 from the OR wire, what comes out?
1.
Yes, and that is the correct sum digit when P is O and Q is 1. It's going to work also when P is 1 and Q is O, because AND doesn't care what order the input comes in. So the AND is going to still output an O, and the NOT's going to flip that to a 1. The OR gate is going to output a 1 when we input P equals 1 and Q equals O. And now again, we have a 1 ANDed with a 1, and we get the correct sum digit as output. And finally, the problem that was really kind of forcing us to work so hard when P is 1 and Q is 1, let's just double check that it really works out. The AND output is 1, and that is the correct carry. The OR output is 1, that wasn't right, but the NOT gate flips the 1 here to an O, and when we AND those together, sure enough, we get the correct sum digit in the case that we're trying to add 1 plus 1. So it works in all 4 cases. So the notes that are posted are a little bit more complete, but the point is we use a NOT gate to temper or change the output of this OR gate. With a final AND gate. And that gives us the correct sum. So this, my friends, is called a half adder. It adds 2 binary digits correctly. And so that's our definition. A half adder is a circuit that adds 2 single binary digits P plus Q and outputs the correct result. CS, where S is the sum digit and C is the carry digit. Okay. So we've got our first little machine that actually does work. Now we want to up the ante because, as we know, when we're adding numbers, it's generally not just 2 single digits, right? We want to be able to add long numbers, and we'd like to be able to add an arbitrary number of long numbers. So there are different ways to up the ante here, okay? We can change P plus Q to maybe a 2-digit number added to a 1-digit number. That would be one way to up the ante. Another way to up the ante is to actually try to add 3 single binary digits. So, I mean, we have a choice about the way that we proceed. So we're going to try to add 3 single binary digits now. And we have a new circuit that we can use. It's called the half adder that does the work of adding 2 binary digits. We're going to be able to use that because it's just like coding, folks. When you build a module that you then call into another larger program, that module's already built and you can just use it. Well, now we have a half adder that's already built and we can use it to build other circuits. We're going to use it now to build a different kind of adder that can add more. We want to add 3 binary digits. So now we would like to add 3 binary digits. Let's think about that. Our goal here is to use the half adder and any other gates we need. And I'm talking about, you know, the AND gate or the OR gate or the NOT gate to build a circuit that adds 3 binary digits. No, 3 that adds, I put the word 3 for an S, that's funny, adds 3 single binary digits. All right, so what does that look like? Let's just look at this. So P plus Q plus R. We'd like to add those, okay? And get a sum and a carry. Now, before we get into this, let's just think about addition and what we understand about addition. Like if we're adding 9 plus 6 plus 7, I'm going to put a little room between the 6 and the 7 in decimal, right? We add the 9 plus the 6 first, don't we? Addition actually happens 2 digits at a time, always. So when we add 9 plus 6, we get 15, right? The 5 is going to get added to the 7. And the 1 in 15 comes to the next column over, 1 column to the left, as a carry, right? Then we actually add 5 plus 7. And we get 12, but the 1 from the 12 comes over here. So we have a couple of 1s over here. Now you might do this in your head. You might say 15 plus 7 is 22. In, any way you slice it, we've got 2 carry digits over here, a 1 plus a 1 to get 22. So there are a couple of things to take away from this just little example. We add digits that are in the same column together. When we add 2 digits and we get a sum digit like the 5 and a carry digit like the 1, the sum digit stays in the same column with the digits whose sum produced them. This 5 was produced with this 9 and 6 being added together. The 5 stays in that column. The carry digit from an addition operation always sits 1 column to the left. So the 1 in the 15 sits 1 column to the left. We call this the tens column in decimal. Okay. So let's just think about adding 3 binary digits. You know, what really happens when we do that? Okay, so let's say that we have P plus Q first, and then we're going to add the R in a minute. When we add P plus Q, we get a sum digit, I'll call it S1, and a carry digit, I'll call it C1. The sum digit is in the same column with the P and the Q. So when we get ready to add R, the R gets added to the sum digit, and it produces a second sum digit, call it S2. But there might be a carry from adding those together, and we'll call that carry 2. And then these 2 carries now need to be added together, and they're going to produce some value. And what I want to explain to you tonight is when these are binary digits, when P and Q and R are just O's and ones, these two added together will never have a carry other than 0. They would only have a trivial carry. So we really only need one digit here. Why would that be true? This is what I want you to notice, is that these two carries, C1 and C2, cannot both be 1. In other words, we're not going to need a third digit over here. Let's discuss why that's true, okay? How do I know that when we add 3 binary digits that these two carries cannot possibly both be 1? Well, let's think about it. Let's say that this carry 1 is 1, okay? What would we have had to be adding together to get a carry of 1 here?
They both would have had to been 1.
That's right, Edwin. The only way we get a 1 here for this carry would be if P and Q had both been 1. Everybody with me? So when P and Q are both 1, what is this sum digit going to be?
0 or
Yeah. Yeah, when we add P plus Q, we get 1 O. So the only way that we could be getting a 1 for carry 1 would be if someone is O. You see? And if someone is O, it doesn't matter if R is O or 1. O plus I don't care is never going to have a carry of 1, is it? It would have a carry of O. Right? O plus 1 has a carry of O. O plus O has a carry of O. See what I'm saying? So if carry 1 is 1, carry 2 has to be an O. And if carry 1 isn't 1, that means it's an O, then this note that C1 and C2 cannot both be 1 is still true, because that's the assumption that carry 1 was an O. So no matter how you slice it, folks, when we add these two carries, when we're adding 3 binary digits, P, Q, and R, we're not going to need a non-trivial carry. And in fact, an OR gate will suffice to add carry 1 and carry 2. Because all we got to do is detect whether one of them is a 1. They won't both be a 1. My point is this. We can use a half adder to add P plus Q. Then we have this sum digit that has to be added to R. We can use a half adder to add them together. But these two carries don't require a half adder. A half adder's got how many gates? Do you remember how many gates that half adder that we just built had? Had 4 gates. Why use 4 gates to add carry 1 and carry 2 together when an OR gate, a single gate, will suffice? So we don't use a half adder when an OR gate will work. So here's how we're going to build the machine that's going to add together 3 binary digits, P, Q, and R. Again, here we can see it here. The P and the Q are in the same column, and we have a machine that will add them. It's called a half adder. So let's put the P and the Q through a half adder. I'm going to make the half adder kind of skinny. Otherwise, this thing's going to get way too big. Now the half adder is going to output a sum digit, sum 1, and it's going to output a carry digit, carry 1. Here's the sum 1. Carry 1 is always 1 column to the left. Now, we need to add this sum digit, just like we had to up here. 9 plus 6 was 15. The 5 still needed to be added to the 7. So this sum digit still needs to be added to R. So we put S1 and R through a half adder. That's what it does. It adds 2 binary digits. So we can put them through a half adder. You can just draw a box and write half in there. And that half adder is going to output sum 2, and that's our final sum digit. That is the S that we're trying to get, you see. But it also outputs a carry digit, carry 2. and we have the carry 1. So we bring them together, but we know they cannot both be a 1, so an OR gate suffices to give the correct carry digit. This, folks, is called a full adder. So if we want a formal definition of a full adder, we have one now. A full adder takes 3 binary digits as input and outputs their sum P plus Q plus R equals CS, where S is the sum digit and C is the carry digit. So we now have 2 circuits that actually do work, a half adder and a full adder. Okay. Questions so far? Well, let's see how far we can get with them. I mean, like, the game here is we really do want to do binary addition, right? Well, we have half adders and full adders. So, I mean, inside that world, which is fairly limited, but it's still a place to start if you want to see how circuit construction actually makes something productive. We can go ahead and start with our first example. And I do have a little recap that I'm going to put in the notes. The recap is, hey, a half adder adds 2 binary digits and a full adder adds 3 binary digits, okay? So armed with that, we're going to now try to draw a circuit that really does some work. More work. So example 1, there's going to be room for the recap here, but I'll just go ahead and put this here. Example 1. The notes are already posted. We're going to draw a circuit that uses only half and full adders. No other gates. We're just going to use half adders and full adders. Because when we get into multi-digit binary numbers, it gets really difficult to see if an OR gate will suffice to add the last 2 carries. So we'll just go ahead and just use half adders and full adders, and produces the correct sum of the binary numbers. I'm going to show you how to do it. So each variable, each var, I can say var, right, for variable, we're all computer science people here, is a binary digit. Okay, so here we go. We're going to add together a binary number XYZ. So this is a 3-digit binary number. Now, just for reference, so you understand, in binary, the base is 2, not 10. Like, if this was a decimal number, the Z would be in the ones place, the Y would be in the tens place, and the X would be in the hundreds place, right? But we're playing in binary. So the Z is in the ones place, the Y is in the twos place, and the X is in the 2 squareds place. Not the 10 squareds place, but the 2 squareds place. And we're going to add to that PQ, and we're going to add to that a number TV. So we want to add together 3 multi-digit binary numbers using just half adders and full adders. Now I want to show you the work on the side, because as we go through this, we're going to be producing sums and carries sort of inside the process, and we want to see where they go. So I'm going to write X, Y, Z here but I'm gonna skip a little space here so that there's room to write what happens in between. So we're gonna think it through here and draw the circuit at the same time. Again, things to remember. There are 3 things to remember. We only add digits that are in the same column, right? Like if you were adding 529 to 67, you would not add the 5 plus the 2 plus the 9, right? We understand that this 5 is 500. It doesn't get added to this 9. The 7 and the 9 are both in the ones column. They're in the same column. They get added together. The 2 and the 6 are in the tens column. They get added together, right? And then any carries might be coming over here and get added to the 5. Well, it's the same way with any kind of number system. I don't care if it's base 10 or base 2. We're not going to add across. We add down inside the same column. So let's just take a look at what needs to be done. We start in the rightmost column. And we're going to add Z plus Q plus V. And we have a machine that can do that. What is the circuit called that can add Z plus Q plus V, folks?
Full ladder.
That's a full adder. So normally, you know, when we build a circuit, we put the input wires in alphabetical order, but that's not what we're going to be doing here. We're going to be looking at the order that the digits are in according to the column that they're in, starting with the rightmost column. So we're going to start with Z and Q and V, and we're going to run these through a full adder. I'm going to make the full adder kind of skinny just so that I don't run out of room. Okay, they're going to run through a full adder. And a sum digit, S1, is going to come out, and a carry digit, C1, is going to come out. Well, the sum digit belongs in the same column where it was generated. The sum digit always stays in the column where it's generated. So this sum digit is actually the final output for this column. It goes right there. But the carry digit, it goes here in the column 1 to the left of the column of the digits that generated it, right? So this carry 1 needs to be added to the other things in the 2's column here. So we can add carry 1 to Y, and we can actually also add it to P because we can use a full adder, but we don't have an adder that adds 4 binary digits. So we have to first add carry 1 to the Y and the P. So we're going to put the Y and the P input wires, and we'll just bend the carry 1 wire. We'll just dog leg it. And we're going to run these through a full adder. Everybody with me? Now, the output from the full adder, just like from any adder, well, there's a sum digit. We'll call it S2. In fact, I'm going to put the carry digit on top. There's a sum digit, S2. I'll put it down here. And there's a carry digit, C2. Now let's go over here and let's write where they belong. Let's put where they are. This sum digit stays in the column with the digits that generated it. So the sum 2 digit is sitting here now, below the C1 plus Y plus P, right? It's going to have to get added to the T before we're done with the 2's column. The carry digit, C2, goes 1 column to the left. It's going to eventually get added to this X. Any questions so far? All right. Well, sum 2 needs to get added to T, and it's only 2 digits, so we can actually use a half adder to add S2 with T. And the output, well, there are 2 digits coming out. I'll put the sum digit on top this time because I just want to get it out of my way. That is the final digit for this column because there's nothing else that we need to add to the S3, right? We're done with this column. Carry 3 goes over one column to the left of the column that generated it. It was generated adding S2 plus T. So carry 3 is over here in the column with the carry 2 and the X. Questions? We're almost done. What's the last input wire that we need now? We're done with the ones column. We're done with the twos column. We're working in the fours column. We've got this wire with carry 2 on it. We've got this wire with carry 3 on it. What else do we need to input now to finish this?
X.
The X. Now it's time finally for this X. It's way over here in the leftmost column. It's going to get added with some carry 2 and carry 3. What kind of gate do we put it through? What kind of circuit? A full adder. And out comes S4. That's the fourth sum we've generated, and C4. And I'm circling them because these are final outputs. The S4 stays in the column that generated it, and the C4, of course, is one column over, but there's nothing there to add it to, so we just bring it down. And this is a complete show of the work. We've drawn the circuit, and we have indicated the indexed sum and carry variables here in the correct order that actually creates the correct sum. I'll show it to you in color. I'm actually, the notes that are posted are a little bit better. They're a little color coded, see. Z plus Q plus V created sum 1. Carry 1 had to go through a full adder with Y and P, creating sum 2 and carry 2. So that's in red, sum 2 and carry 2. Then sum 2 and T got added together with a half adder, creating sum 3 and carry 3 in black. And then carry 3 and the X went through a full adder with the carry 2 to create sum 4 and carry 4, which are in green. Okay, so that's the notes that are posted. They're a little bit color coded. It makes it a little easier to see. Any questions? You want to do one? Let's do a bigger one. And this is challenging because if we were in the same room together at this stage, folks, I would be I'd be walking around and looking over your shoulder and kind of correcting you. And it's hard for me to do that while we're, virtual, right? So you can work on it if you want. You could drag into the chat a picture of what you're working on if you have the machinery to do that, and I can look at it. But meanwhile, let's just work on one together. If you want, if you can figure out a way to do that, that's fine. I can look in the chat. Here's example 2. I want you to build the circuit and indicate, just like we did in this example, which I can put back up, by the way, exactly where your output digits go, where your output digits belong in the final answer, just like we did with this other example. So like I said, I can put it back up. So here we go. It's going to be XYZ plus PQR plus TUV. And I'm not indicating how many digits you might need in your final sum here because I kind of want you to work through that. And like I said, I'm going to go ahead and display the work from the problem that we just did as a reference. Showing the work like I have done here is going to be really helpful when you do this. So like over here, when you're showing the work, you can put X, Y, Z, but make some space because you might have to put a carrier or sum between that and P, Q, R, and make some space here, and T, U, V, just so you have room to put your carries and sums in here, okay? As you work. So this would be a show of the work here. So go ahead and get started, and I'm sitting right here to see if anybody has any questions. Just remember the facts. There are 3 facts. You only add up digits that are in the same column together. The sum digit stays in the column with the digits that generate it, and the carry digit goes 1 column to the left of the digits whose sum generated it. It's 3 simple rules. So like I said, I can look for the chat. If it's easier for you to email me, it's going to be difficult for me to open my email while I'm online, but I can try. But you could email it to yourself and drag it into the chat. Why don't you do that if you want me to take a look at what you're doing? And I can open a PDF. I can probably even open a JPEG. How you doing, Stephen? Hussein, can you check the chat? I think I sent the wrong, there we are.
I thought I had it on. I don't know why I was off.
That's okay. Just want to see you. Let me ask you this, as you go through this, can I ask y'all, are you adding Z plus R plus V first in a full adder? Is everybody doing that? That would be the first step, is to add Z plus R plus V with a full adder, right? Good, thank you. I appreciate the chat in. Like I said, that's Marcus, right? Yeah, good, good. And F to everybody. Is that, let's see, who is, oh, that's you. It's the same, okay. Mina Lopez, thank you for saying yes. So you can chat in questions, or again, if you want to drag an image into the chat, if you want me to look at it. So I think we all know that the first thing we're going to do is we're going to add Z plus R plus V. So I'll draw that much of it. Z and R and V go through a full adder together. And S1 is the output digit there, right? And carry 1 is over here above the Y. right? Let me just ask, is anybody trying to feed carry 1 and Y and Q and U all together into one adder? Can we do that? Can we put 4 input wires into one of the adders that we have? We cannot, right? The most input wires that we can draw into one of our adders is 3, right? A full adder can handle 3 inputs. We do not have an adder that can handle 4 inputs, so we can add C1 plus Y plus Q, right? We can put the C1 that's coming out of here, sorry, with a Y and a Q through a full adder, but we cannot add the U in there, just the Y and the Q. How many people have gotten this far? Anybody gotten this far? But S1 is not a final output digit. It's right here above the U, see, right? Nice. Oh, okay, good. Somebody's attached something. Let me take a peek. Let me look at that. Oh, can you, oh, wow. Let's see if I can rotate it. Oh, I can rotate it. All right. Let's see if I can make it bigger so I can see it. Trying to see it. I'm gonna download it. Oh man, I'm so sorry. I cannot see that. It's just too small. Maybe I can see if I look at it sideways. That looks right. Oh, good job. Nice job. Yeah, that's right. C6, S6, S5, S3, S1. Yeah, that's nice. So if you are, if you have been able to draw this circuit, then go ahead and open special homework number 3, and you can start working on that now while we're all together. And the rest of us, we can still work on this. Oh, this is an S2, my bad. This is an S2. Sorry, this is a 2. I did that earlier today. This is a 2, right? We have to up the ante. We have to change the indexing. And here's C2. And S2 gets added to U. With a half adder. And we output S3. So the S3 goes here. But C3 has to go over here. And C2 is over here as well. So you have a C3 being added to X and C2. Would it be S4, S3? No, the S4, check it out. Did you get S4 by adding C3, X, and C2? That's how you should be getting S4, is by adding this carry from adding S2 to U and the carry from adding C1, Y, and Q, which is C2. These two carries get added to X. But look, that sum digit that comes out of that full adder from adding X to these two carries, that sum digit belongs with the P and the T still here in this fours column. See what I'm saying? That's not a final output. So it's not S4, S3, S2, S1. See what I'm saying? The S4 that comes out of this full adder is still in the column because P and T are still in that column and they still need to be added to something. See? Does that answer your question? Okay, good, good. Right. So the C4 is going to be over here, but the S4 and the P and the T now get added. Now that finishes up this column. S5 is what the final output is in the fours column. But C4 and C5 are over here in the eights column. And they have to go through a half adder to get S6 and C6. It's S6 and C6 that are the final output digits there. You see that, folks? Questions? This is going a lot faster than it went in-person class because I really was wandering around and kind of over people's shoulders. This format does not lend itself to that very much. But how about we take a look, raise your hand if I'm going to go to gallery view. Raise your hand if you have any questions on this. Like, how many people were able to get the right circuit, or at least you feel like you're on your way? Danny, Marcus, Stephen, good. Eric, Matthew, Nick, Gabriel, Deontay, Mina Lopez, and Kendall. Great. Nitty, I can't see ya. Hossein, got it. Great. Kenneth, what can I do to help?
I think I just need a little more practice with it before I feel a little more comfortable.
Yeah, it's a process, but keeping things, like keeping track and putting your intermediate values, like your carries and your sums, in the next column, like spreading it out. Yeah, good. Okay, yeah, it takes time. It takes time. I'm going to navigate to the homework, and I'm going to share my screen here in just a second, so that we can spend a little time looking at the homework that's been posted, because I just want to make sure everybody's on the same page with that. It's not that often that we have a little extra time to kind of work on problems together. And I'm going to share my screen here. Check it out. Here in the good stuff folder, like I said, there's this new folder called worksheets for extra practice. Like, for example, maybe you feel like you need some more help with negating statements. So there's a worksheet and a solutions. So you can like work the worksheet. You don't have to print it if you don't want to, but you can see the problems. Right, it's a whole bunch of problems to practice on negating, and then there's the solutions file, so you can work on them and then you can check yourself, or you can come to office hours, right, and check if you're not getting the same solutions that are there. Okay, And then there's a worksheet on the conditionals and the biconditional, right? The sisters. So here's a worksheet on the if-then statements. So this worksheet is just circle all the statements that are logically equivalent to the statement that's given initially. There might be more than one. So there's 3 examples there to practice equivalent if-then statements, okay? And the solutions are there. You know, you can click on this and see the solutions after you do it. And there's a worksheet on logic, and it actually includes another circuit problem. Okay. And this one is just understanding how to and or a tautology with a contradiction. Here's one to draw the circuit. Okay, and then I ask a question about drawing it with fewer gates. Let's look at the special homework that's due next week. It's special homework number 3. Let's just look at that together. Okay, so a little, information on the slight upgrade again to, saying, hey, this work is my own. That's the little academic integrity statement you're going to include on your cover sheet. So the first problem is to draw a circuit that goes with this Boolean expression. Does anybody remember the name of the form that goes with this Boolean expression? We learned that last time. Anybody remember the name of that special kind of form? Where it's, go ahead. Sorry, go ahead.
Undisjunctive.
Yeah, it's disjunctive normal form. So I ask you to draw the circuit. We're going to call it circuit A. Okay, so you're going to draw that. And then you're going to construct the IO table. But we know that when the expression is in disjunctive normal form, it's really pretty easy to create the IO table, right? We talked about that at length on Monday. Now, in problem 2, I give you a new definition. What does it mean for 2 circuits to be logically equivalent? Well, it's just what you think it should mean. It means their IO tables look exactly the same. In other words, they output a hot wire on the very same input states. So one of the ways we measure efficiency of a circuit is by counting the number of gates in their circuit diagrams, in their circuits. And so if circuit A and circuit B are logically equivalent circuits, then naturally we want to build the circuit that uses less raw material. We want to build the more efficient circuit. So here's another Boolean expression. Now this Boolean expression is not in disjunctive normal form, because although there is an OR operator there, the expression here to the left of the OR operator is not a complete description of all of the input variables. It just tells us about P and R both being hot. It doesn't mention Q at all. So you're going to draw the circuit for that Boolean expression, and we're going to call that circuit B. And then you're going to construct the IO table associated with this circuit by running the 8 different possible inputs through the circuit. We did this in class. It's time consuming, where you actually run the values through the circuit for each possible input state. And that way you create the column for the output S. Okay, so you're going to do the long way here for 2B. But 2C asks you now to compare the circuit from problem A with this new circuit in problem B. Are they logically equivalent? Well, just refer to this definition. 2 circuits having the same inputs, and these have the same inputs, they have P, Q, and R for inputs, are logically equivalent if their IO tables are identical. So you're going to compare the IO table that you built for circuit A in problem 1 with the IO table for circuit B. And if they're identical, then you're going to say, yeah, they are logically equivalent. If they're not, you're gonna say no. And then you're gonna explain why, if they are logically equivalent, and state which one of those two circuits is more efficient using the measure where the fewer the gates, the more efficient. Questions? So I'm trying to teach you some new stuff kind of on the fly, where, you know, the idea of logically equivalent circuits and the idea of efficiency. Now, listen, there's lots of ways to determine efficiency. Counting gates is not necessarily the way that you would define efficiency. You know, fewer gates equals more efficient. Because in real life, actually, AND gates take less time to process than OR gates, believe it or not. But a simple first measure of most efficient is simply to count the number of gates. For problem 3, I've just described a circuit and asked you to build it. So I've just described what the circuit does. It's going to have 2 inputs, P and Q, and we want the circuit to output 1 if and only if P have the same value. And then I ask you this question: what logical expression does that circuit correspond to? Because we've learned some statement operators like the if-then operator, the not operator, the and operator, the biconditional operator, the or operator. And I'm just asking you what logical expression a circuit that does this would correspond to. So you can think about that and review the operators that we've learned. And then finally, the last problem is to use half adders and full adders, just like we've done tonight, to add up these 4 binary numbers. It's a 3-digit, a 2-digit, and a couple of single-digit binary numbers. So that's the special homework that you can be working on. And we've still got like 7 minutes of class. I have presented all that I'm going to present for tonight, but I'm going to hang around. And if anybody has any questions, if you want to look at some of these homework problems, we can do that. Or if you want to practice some more of this, I will hang out. Otherwise, you are free to go. Class dismissed. But I'm going to stick around. I'm going to stick around and see if anybody needs any help.
Have a good night.
Have a good night. I hope you enjoyed it. I hope you had fun.
Yeah, it was cool.
Thank you.
Oh yeah, I got one question from last class.
Uh-huh.
Did you ever regrade the special homework or not? You didn't get to it yet.
I graded special homework. Did you turn yours in late?
Remember last class? I had a conversation. I had to turn it in again because of something that had happened on my file, and you wrote a note down.
Yeah. Yeah, I do
Yes.
have that note here that I'm going to regrade it. I haven't gotten to that yet. It's been pretty busy since Tuesday. I mean, since
Okay.
Monday.
Okay.
I'll get
I
to
was
that.
just-
I'll get to that this weekend.
All right. Thank you.
You're welcome. Yeah, I've got your name down, written down, and somebody else's name written down for that.
How you
Nick?
doing, Professor? I wanted to know, did you see my message? And I had submitted the homework in with the note.
Did you send me an email with special homework 2 in with the note?
I sent it to Blackboard because you told me resubmit it through Blackboard again.
Yes. So I'll get to that this weekend. Yeah, I saw.
Okay, I put the note in.
Well, listen, can you
Okay.
just upload it where it belongs? Would it not let you upload it where it
Yeah,
belongs?
No, I uploaded it to Blackboard.
Okay, well, I haven't graded those yet. But if you
Okay.
uploaded it, it's there. You want me to check and make sure it's there?
Yeah, I uploaded the special homework too. I uploaded the homework and then the paper.
You uploaded the homework in the what?
In the note. The note for excusing my absence.
Yeah. Yeah, I see 2 attempts here. And
Yeah, it's on the
yeah, you've
second
got a
attempt.
note and the homework. That's fine. You're good. That's fine. Yeah, I'm so sorry. I'm so sorry. You must have had a tough weekend. I'm very sorry. But yeah, I see your homework here.
Okay,
looks-
thank you.
It looks
Appreciate
great.
it.
Looks great.
Thank you.
Yeah, I'll be grading those this weekend.
Okay,
Thanks for double checking.
no problem.
Hey, Nick.
Hello, I do have a question about the section 2.4 homework you put up.
Okay.
Question 4, I don't know if we went over it. I tried going through the different inputs and outputs and comparing it to the Boolean expressions, but I'm just really confused.
Okay.
If you want me to share my screen, I can do that.
Yeah, you can share your screen. Oh, go ahead.
All right.
Or I can get in there, and we can look at it together.
Let's see.
It's problem number 4, you said?
Yep.
All right. All right, you're gonna have to make that. Okay, so you got to make that bigger. All right, I'm gonna look at it on mine, okay?
Okay.
Because for me to see it, I got to look at it on mine.
Okay. Do you want me to stop sharing?
It's okay. You can just keep it up.
Okay.
I'll look at it on this screen. And so the point was, you tried to write the Boolean expression, but you couldn't pick the right one. Okay, that was problem 4. Where you're
Yes.
trying to pick the Boolean expression. Okay, no problem. Hang on. This is section 2.4, right?
Yes.
All right, so in problem 4, they give you an IO table and they say, which of the following Boolean expressions has the given table as its truth table? All right, so this is the deal. You look in the column for the output, all right? And you look for where the ones are. Okay? The ones tell you that in that row, that input describes a hot output. So for example, do you see that there's a 1 in row 2
Yes.
for output? Now we did go over this at length. If you go back and look at the lecture, we described what each row input would be written as. So in row 2, CP has a 1 and Q has a 1 and R has an O.
Yeah.
So the way that we write that as a Boolean expression is P and Q and not R.
Mhm.
See what I'm saying?
Okay.
So that's one of the possible expressions where you get an output of 1. So you would write P and Q and not R in parentheses. But that's not the only time that this circuit is going to generate a hot output. Look in row 4. See, in row 4, the output S is 1.
Mm-hmm. I see it.
So now look at the input in row 4. Can you tell me the expression for that input state?
Row 4. Would that be P, not Q, and R? Right?
Well, I see an O under R.
Wait. Sorry, I'm reading the one above. P, not Q, and not R.
Yeah, and it's ands between those because they all have to happen at the same time. So row 4 is P and not Q and not R. So either row 2 or row 4 should produce a hot output, or row 6. See, this is going to be disjunctive normal form. There's going to be ors between the parentheses expressions. So what does row 6? What is the input state in row 6?
What is that?
Because that's the other one is in row 6. The
Not
output is
P,
1.
Q, and not R.
Not P and Q and not R.
Q and
So
not R.
you take those 3 parentheses expressions, the one for row 2, P and Q and not R, and you put an or between it and the next one, P and not Q and not R, or, and then parentheses, not P and Q and not R. See what I'm saying?
Yep.
Because, right, you just look for where the output S is hot and you write down the input state for that hot output and you OR them all together across, the many rows where you might have a 1 for output.
Okay.
And we did discuss this at great length, actually, in the last lecture. Were you there?
Yes.
Okay, but I'm glad you asked. And so then you pick the circuit that actually will do that work. And one of the things that's nice, if you look at this disjunctive normal form, do you see how the last operator that actually gets executed is the or operator that's in between the parentheses?
Yes.
See, or happens last. And so when we have disjunctive normal form, we know the last gate is going to be a big old or gate. So that automatically allows you to toss out a couple of the choices. Because you know the last gate that's going to get executed is not going to be an AND gate. It's going to be the OR gate that goes between the parentheses.
Okay.
So that already narrows it down. But then inside parentheses, right, like in row 2 of that IO table, you have a hot output. You have a 1 for S, right?
Mm-hmm.
So P and Q and not R, those all have to be getting ANDed together. You need P ANDed with Q, ANDed with not R. So there's going to have to be an AND gate that accepts the P wire, the Q wire, and a not R wire. There's also going to have to be an AND gate that accepts the input from row 4, because that's another row. Why don't you stop sharing for a minute, and I'll share. Okay, so we look where the ones are. See, there's a 1 in row 2. So P and Q and not R. So there's going to be an AND gate that accepts P and Q and a not R. So you're looking for an AND gate that accepts P and Q and not R. See, there's an AND gate right there that P is feeding into and Q and not R. Now in row 4, I mean, you may have a different problem than me because maybe that it mixes up the problem a little bit, right?
No, they look.
Does your problem
Look
look
the
the
same.
same as mine?
They look the same.
Okay, so in row 4, P is getting ANDed with not Q. See, everything's happening at the same time in a single row. That's why we use an AND across the row. P gets ANDed with not Q, gets ANDed with not R. So there's going to be an AND gate for P and Q, not Q and not R. So P and not Q and not R gets ANDed together, see?
So it has to be 3 AND gates and then an OR gate at the
And
end. It's all-
right, and then an OR gate at the end.
Okay.
Because the ORs are what happens between the rows. It's this row gives hot output, or this row gives hot output, or this row gives hot output. Okay,
Okay.
great. I'm so glad you asked.
Thank you.
You're welcome.
Have a good night.
You as well.